Hey guys, so I've been getting this question a lot recently, and it's how do we get to the exponential form or Euler's form of the complex number? And just a reminder, if z is some sort of complex number, then Euler's form or the exponential form is r times ej theta. And it makes sense that the professor wouldn't want to derive this in their lecture notes because it's kind of a long process, but it's not the most difficult to understand, and it's really interesting. So I'm going to get right into it, and it gets a little bit ugly, but it's not the most difficult, and if you stick with this and I have your attention, you will understand it too, and it's a really cool derivation. So we're going to start off with the standard form of z, a plus bj, okay, where a and b are real numbers. Great. And I'm gonna represent this on the real and imaginary axes. This being my imaginary, this is my real. And we're gonna draw some arbitrary vector representation of our complex number z plus bj. And I know that this will be the distance a, and this will be the distance b. So I can draw a little right angle triangle off to the side here. And I know that this will be the modulus of z, which is r. This will be b. This will be a. Great. And then this angle that I make with the real axis will be theta. Let me draw that too. Great. So then, using just basic SOHCAHTOA, I can show that a will be equal. And let me use a different color here. A. Let me change that as well. Will be equal to r times cosine of theta. And I know that b. I'll change this as well. B is going to be equal to r times sine of theta. So then I've got the form z equals a plus bj. So let me just replace these values. I've got r cos theta plus j times r sine of theta. And you'll see I can factor out the r from both of those terms, and that leaves me with cosine of theta plus j times sine of theta. And you'll see that this is polar form, right? And polar form is really crucial to understand. I've noticed that a lot of people are just kind of not understanding where it comes from, but we're just writing it the standard form, but in terms of the length of the vector and the angle that it makes with the positive direction of the real axis. Sweet. So I'd like to introduce you guys to a little bit of a new concept that some of you might know, and it's called polynomial approximation. Polynomial approximation. And it's basically saying that any sort of function that I have, I can actually represent that with a polynomial if I make the degree go high enough. And I'll show you a little bit what I mean. So let's take an example with let's say a trig function, like a sine. Okay? So let me write out sine. It looks something like this. Right? This is y is equal to sine x. Okay? And then this is my y. This is my x. Great. And let me draw something that looks kind of similar. I'm going to draw a polynomial that's to the third degree. Okay? And it's going to look something like this. Right? That looks like a polynomial. So this is some sort of polynomial to the third degree, okay? Let me just write this out. a third degree polynomial. And I don't know what it is, but I could have a third degree polynomial that looks like that. It's got 3 roots. So you'll notice here that this section right here that I've just highlighted, that looks very similar to this section of the trig polynomial, or of the trig function, right? And what I want to show you is that, so if I were to go to a higher degree and I increase the number of degrees, then I could theoretically make something that looks kind of like that, right? That's just some random example. So this polynomial would be how many roots? 1, 2, 3, 4, 5, 6. I've got 6 roots, so this could be like a 6th degree polynomial. Looks something crazy like this, maybe even higher, right? So this is increasing the degree of the polynomial, and you'll see that it starts to even more accurately represent this this trig function that we have, right? It's looking more and more like it, and I want you to recognize that if we increase the degrees of our polynomial, then we can model another function very, very accurately. And if we were to increase the number of degrees to infinity, we can actually not even model these other functions, but they can turn into these other functions. Like I can write sine of x only with polynomials, but if I say that I'm going to turn this polynomial and make it go all the way to the infinitieth degree, then it will actually be sine x. It's not going to be an approximation, it will be sine x. And that's really, really cool. So what I want to do is I want to find what that polynomial is. And this is something that you'll learn in probably your second term of first year, or maybe even the end of your calculus term for this first term. But there's these things called Taylor series expansion, and actually I think some people in AP might have heard of these. And a Taylor series, a series is just something that it's something that we're going to sum, and it means that we're going to take the addition of something, and it can be something with x's or variables, and we can make it go to infinity if we wanted to. So this Taylor series expansion, it can be written like this, and bear with me if you haven't seen this notation before, because it's not the most important. Like, if you're not learning this in your course right now, it's okay, but you do need to know it for this proof. And this is basically saying that I'm going to sum all of the numbers from starting at n equals 0 to infinity of some function f of x that is centered at x is equal to a. So this is going to be a Maclaurin series, so we're going to say that x is equal to a, which is equal to 0. So it's going to be, we're going to center our function at 0, and then this f to the n of a, it means the nth derivative of a. And it's okay if that doesn't make any sense to you, but it is going to be important for this proof. But what we want to do is figure out how can we write a Taylor series expansion for sine and cosine, because that's what I've got. That's what I have in my my polar form up here. I've got r cos theta plus j sine theta, and I want to rewrite cos theta and sine theta in terms of a polynomial. So let's figure this out. First, let's do f of x is equal to, let's do for sine of theta. So for sine of theta, and we're just going to say that x is theta because it's easier to read. Okay, f of x is sine of theta, I know this. The derivative of this is going to be cosine of theta, or cos x. And I'm going to keep taking this derivative a bunch of times. Sine x. The third derivative will be minus cos x. fourth derivative will then go back to sine of x, and then the fifth it's going to start, you're going to see that it starts to repeat itself. Okay? So now if I were to write this sine of x as this expansion, this Taylor series expansion, then using the formula, I'm going to start at n is equal to 0, and then the zeroth derivative is just the function itself. So it'll be sine of, and I'm saying this is centered at 0, so sine is 0, and then this will be x minus 0 to the power of n. And just a quick correction, actually. This should not say x is equal to a. This should just say a is equal to 0. That's what we're centered at. So then I'm going to add the next term. So n is now equal to 1. So this will be a 1. And then the first derivative, so that I've calculated that to be cosine, and that's of 0, x minus 0 to the 1. And sorry, that first one should read 0. Great. So then my next one, I know that my second derivative is negative, so that'll turn this into a minus instead of a plus, right? Plus times minus will be minus. And I'm going to keep on writing this out, okay? Sine of 0, x minus 0 squared. This will be minus 3. And this is cos of 0, x minus 0 to the 3, plus 1 over 4 factorial, sine of 0, x minus 0 to the 4, and this is going to keep going. So when I'm evaluating this, let's take a look. Sine of 0 I know is going to be equal to 0, so that means that all of these even terms are all going to cross out, right? So if I were to rewrite this now, sine of x, this is going to be equal to the first term. I've got cos of 0 is 1, so this will be 1, and then just x, 1 times x to the 1, right? I'm just going to keep this form, and it'll make a bit more sense. My next term I've got to the power of 3, which is 1 over 3 factorial, and then x is to the power of 3. If I were to write this for the fifth, it'll be x to the 5 over 5 factorial. And if I were to keep going, it'll look something like this, right? That's what we've got. Cool. And if I go to infinity, this is equal to sine of x. And you can, if you don't believe me, go to Desmos and start doing this until you get to like the 50th degree or the 25th degree or something. But once you get up there, you'll see like, wow, this starts to look exactly like sine of x. It's kind of crazy. So if you were to follow the exact same process for cosine of x, you would get 1 minus x squared over 2 factorial, and then plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, plus x to the 8 over 8 factorial, and then that would go on to infinity. And that would be our representation of cosine of x, right? And now this is going to get a little bit ugly here, but just bear with me, guys, okay? I want to take these polynomials that we've just written, and I'm going to substitute them back in for r times cos theta plus j sine theta, okay? So let's write this out. I've got my complex number is r times, and then I had cos theta plus j times sine theta. Great, okay? So now I'm going to substitute these polynomials in, okay? So I'm left with this, okay? And now what I'm going to do is I'm going to distribute the j inside of this sine theta term, and I'm going to rearrange it in terms of the degree, okay? So we're going to do that now. I'm going to start off. So we'll have 1, and I'm just going to rewrite this as x to the 0 over 0 factorial, because that's equal to 1, but I want to write everything in terms of x, okay? And then my second degree, that's going to be, or my first degree will be plus j times x to the 1 over 1 factorial, and then this will be minus, and then I've got x squared over 2 factorial plus, this will be a minus now. I've got minus j times x to the 3 over 3 factorial. And I'm going to keep writing this for all of my degrees, okay? So I've just done this, and there's something that I want you to notice. And this is like not super intuitive, so don't worry, because it doesn't look like we can do anything right now. But you see that half of our terms have j, okay? And you'll notice that the sign of our polynomial is going plus plus minus minus, plus plus minus minus. So let's take a look at something else that we know here, okay? You'll notice that j to the 0 is positive 1. J is going to be just positive j. J squared will be negative 1. J to the 3 will be negative j. And then j to the 4 is equal to 1. And if I could keep going with this, right? J to the 5 would be equal to j to the 4 times j. And if j to the 4 is just 1, then this will just be positive j. And you'll see that this keeps going, this pattern. Right? And you'll notice here, look what we've got. We've got plus, plus, minus, minus, plus, plus, minus, minus, and this will keep going. So what this shows me is that I've actually got some hidden j's in this polynomial. We have hidden j's. So now I want to rewrite this with all of these j's, okay? So I've just moved this to the side, okay? And now let's rewrite this with all of the j's, all of our hidden j's, okay? So we've got r times, and now what I've got is j to the 0 times x naught over 0 factorial. I've got j to the 1, right? And this, keep in mind here, we have a minus, right? Because j squared is minus 1. But if I were to write j squared in this term, then I would be doing plus j squared, because when I sub in minus 1, then it becomes a subtraction. But I'm writing this out with all of my j's, so it looks kind of like this. And I'm going to keep doing that with all of my terms, right? J to the 4, x to the 4, all of this. And that's going to keep going to infinity, right? So we're going to do one little substitution just for readability. Let's let capital X be equal to j times lowercase x, okay? So now I'm also gonna just denote that inside part as some function of capital X, just so I don't have to keep writing out everything over and over again. Okay. So I've just written it out, and now what I want to do is I want to show you something really interesting. We're gonna take the derivative of this, okay? And this doesn't look like super hard to take the derivative of. It's just a polynomial. So we know x to the 0, that's just going to be equal to 1. It's 1 divided by 1, which is a constant, right? So derivative of a constant will be 0. Let's take the derivative of the next term. This is going to be 1, right? X to the 1 is just derivative of that, 1. I'm going to keep taking the derivative. Now I've got 2x over 2 factorial. I'm going to do the same thing with the next one. 3x squared over, and then 3 factorial is the same thing as 3 times 2 times 1, or 3 over 2 factorial, or 3 times 2 factorial. And I'm just going to keep doing this with all of my functions, or all of my terms here in this function. And you might start to notice something. And if you haven't noticed this, let's rewrite this, right? What's 1? Another way I can write 1 is x to the 0 over 0 factorial, right? That's 1. And then my 2 divided by 2 factorial is going to cancel out. So I've got x to the 1 over 1 factorial. My 3's will cancel out. And then I've got this. And take a look at this. I am writing out the exact same function. Isn't that crazy? Like when I first did this, my mind was literally blown away. So I just took the derivative of a function. Let's think. I just took the derivative of a function, and it was the same as the function. And out of all of your years of calculus experience, you know that that only holds true for a single function. That single function is e to the x. That means that f of capital X must be equal to e to the x. Now that's crazy. And then, so putting this back in terms of z, we have r times e to the capital X, and we know that we made that one substitution, that we said that x is equal to j times lowercase x. And then earlier we said that we were just going to use x instead of theta, right? So that capital X is actually j theta, which means finally we get r times e to the j theta. And that is how you get to the exponential form or Euler's form of a complex number.